Welcome back to our videos on the course Measure Theory for Probabilists. We introduced the integral last time. We approximated measurable functions by simple functions. And today we're going to talk about convergence theorems. So basically these are results which allow you to interchange the integral and a limit. So we need a sequence of functions converging to another function. We already know that the limit of measurable functions is measurable. And then we can, under some conditions, interchange the limit and the integral. So let's see what I mean by this. Convergence results. Let's start by stating them. First, for the Riemann integral, you might know a similar result. And so that's the first one here, and the second and the third are for the integral that we are learning here. So for the Riemann integral, where you really have to find points on the x-axis in order to define the integral, and then evaluate the function somewhere in between such 2 points. So that's for the Riemann integral. There you need a sequence of functions, a limit function, and a uniform convergence. So Fn goes to F uniformly. So, okay, uniformly means sup over all omega, Fn of omega minus F of omega goes to 0. Then you have this here, or sorry, Fn of, here it's x, here it's omega, that should be the same. Okay, and for the integral we are learning here, Lebesgue integral, we have the following two main convergence results: monotone convergence and dominated convergence. Monotone convergence is you have functions in L1, so that means they have a finite integral. You have an f, which is just measurable, and the limit here almost everywhere pointwise but upwards. So Fn of omega is an increasing sequence and converges to f. Then the integral converges. And just recall, so this here, mu f, that was defined as integral f of omega d mu of omega, or how do we say that, mu d omega or something. So all this is the same, mu d omega. So that's the same as above here. The only difference is here I have a mu, I have a measure, and here when I write dx, I usually integrate with respect to the Lebesgue measure, meaning that that dx here is lambda dx and lambda is Lebesgue measure. And Lebesgue measure is the measure which just measures the length of the integrals. And here I have a more general version. Okay, so here I had uniform convergence as an assumption, and here I have pointwise convergence, which has to be increasing, which is of course a weaker assumption. And the last one, dominant convergence, which we will use in the probability course very often. That's the following. Again, you have a pointwise convergence, so almost everywhere convergence, as above here. So here we had it increasing. But here we have one additional restriction. We have that the absolute value of Fn is smaller or equal to some g. Well, and the only thing we need about the g is that g is integrable. The g doesn't appear in the result anymore, but it has to be there. Such a g has to be there. Then we can again say that the limit of the integral is the integral of the limiting object. So here the limit is outside of the integral, and here the limit is the f, so it's inside of the integral. These are the two main convergence results that we will have today. Let's just start with the monotone convergence, and let me just recall that we almost had that in the last video. That was this here. Here we had fn is increasing to f, and then the integrals converge. It's slightly less general here because of two things. So first, the fn's and the f have to be positive or non-negative, and it's increasing, not only almost everywhere, but everywhere here. And we have to relax the everywhere part and this positive assumption here. But that's actually not too hard. So let n be in f and a zero set, a null set, mu of n equals 0, and fn of omega is increasing to f of omega for omega not in n. So that's the almost everywhere convergence part. And then I can define Gn, which is Fn minus F1, indicator complement of n. So the Fn's are increasing. That means Fn minus F1, that must be bigger or equal to 0. And it's also an increasing function. And on these Gn's here, I can now use this bit here. So because I only restrict myself to the complement of n, I have the convergence everywhere. And since I have Fn minus f, I have that Gn goes to R plus. So I can use this in the following sense. So so first of all, this here grows to f minus f1, indicator complement of nc. And we have that mu gn converges to, and here for the integral, of course, it doesn't really matter if I exclude a set of measure 0. That does simply not matter. This here converts, according to the other theorem, to mu of g. So when we call this here g, so that's from the other result. And then, what else? We have to compute the difference of the integral of fn and of gn. And the difference is the integral over f1. So this here is mu f1 plus this here. That converges to this here plus mu f1. And then we know that the integral is linear. G f1, so that's the integral of f. And we are done with the monotone convergence already. For the dominant convergence, we have to prove an intermediate result first, which is often also used standalone because it requires a bit less. So here we do not need this dominating function. So this g here, that's the dominating function because dominated convergence dominated by the g here. We do not have this here. And the result is slightly weaker because we only get an inequality. That's very general here. So the limit inside is always smaller or equal than the limit outside. Okay, the lim inf, let's say. Let's prove this. For k bigger than n, we have the following fk is bigger or equal than the infimum over L bigger than FL. Why is that? So k is bigger or equal to n. So this fk is also in this set here. So it's also part of this here. And it can only become smaller if you take the infimum here. So we can write down mu fk is bigger or equal than mu inf L bigger than FL. This follows from monotonicity of the integral. This holds for all k are bigger or equal than n. So it also holds for the infimum of this here. Okay, and now it's the following one-liner. I start with lim inf, n goes to infinity, mu fn. That's, well, just by definition, sup over all n, inf over all k, starting from n, mu fk. We have that this here, the infimum is bigger than this here. And the sup stays outside. Mu inf. Okay, now I write k bigger or equal than n, fk, like this here. And now we realize that this here, as usual, when n is growing, the infimum is over a smaller set, which means this here is an increasing function here. So these are increasing functions. And for increasing functions, we know that the limit, so the supremum, can be interchanged with the integral here by monotone convergence. So this here is then mu sup inf, which is again lim inf, fk, or fn, n goes to infinity, like this here. And we have it already. So here we have the inequality. So that's the lemma of Fatou. Now let's come to the, well, maybe most frequently used convergence theorem, dominated convergence. We already had that. So we need this G here. So in the assumption, and we can now use the G. So how do we start here? Okay. First of all, I would like to say, get rid of this null set where fn is not small or equal to g. And fn converges to f everywhere. If that's not the case, just again, as before, as here, restrict yourself to an indicator of the complement of this null set. And we can, of course, use Fatou's lemma. How can we use it? So first, I can write mu of g plus f. So g plus f is a limit of g plus fn. And lemma of Fatou says that mu of the limit is smaller or equal than the limit of the integrals. So that's smaller or equal than lim inf, n goes to infinity, mu g plus fn. Okay, the integral is linear, so the mu of g I can write down outside this thing here, plus lim inf mu of fn, and it goes to infinity. And in the same manner, I can write down with mu of g minus f. So that's again a limit here, g minus f. Lim inf mu of g minus fn, n goes to infinity, which is then mu of, g minus lim sup mu of fn. So the minus here makes the lim sup from here, as the lim in from here to lim sup from here. Then I subtract mu of g from both things. And then I get well, what do I get? Yeah, here I have mu of minus f is more or equal than minus lim sup mu fn. Or mu of f is bigger or equal than lim sup mu fn. So I can have mu f from the first lines more equal than lim inf mu fn. This is of course more equal than lim sup mu fn. And lim sup mu fn, so when we multiply this line after subtracting the mu of g, so let me just do this here. So I get rid of this here. I have a minus here and a minus here, so I multiply the inequality by minus 1. Then I get a minus here. I do not get a minus here. I get a plus here. I get the other way around here. I get a plus here, which means I can now write mu lim sup is more equal than mu of f. And this means lim inf equals lim sup equals mu, so the limit of mu fn is mu f. And we have proved dominant convergence. Okay, now let's check the assumptions. So first, a very trivial assumption. Fn is 1 over n. Then Fn goes down to 0. I mean, I could also use Fn equals minus 1 over n, which goes upwards to 0. But like this here. So in Fatou's lemma, we have that mu of lim inf is more equal than lim inf of mu of the fn's. And that is true here. So mu of lim inf, okay, that's mu of 0, that's 0. But all the mu fn's here are infinity, because when you integrate 1 over n over the whole real line, then you get infinity. And you have just 0 is more than infinity. Right. Right, and we also have to see that in Fatou's lemma, we also need here, they only go to R plus. Yeah, otherwise the proof here does not work. Yeah. Otherwise the proof does not work, because we did not assume here that they are really integrable, what we had for monotone convergence. So for the monotone convergence we have used here, we required the other convergence here, and where we also used that the functions go to R plus. So that's the reason why also we have here the assumption they go to R plus, and then we have Fatou's lemma. So that's one thing, and the other thing is, in dominated convergence, it's a bit funny, the result, because you have a g here, which does not appear in the limit at all. So you might wonder, do I need the g at all? And yes, you need it. So here are two examples. So the first one is this one here. So I have 0, 1, and in height n, I have here 1 over n, and that's the function fn. When I integrate this, I have, well, 0 to 1 over n, that's has an error 1 over n times n, which is just 1, so the integral is 1. And the pointwise limit, well, it's infinity at 0, and otherwise it's 0. And that's important now, there is no g with fn smaller or equal than g. And yeah, so there's no integrable function which is bigger than all the fn's. So why is that? Let me just try to draw this in a nicer figure. So I have that's one fn here, that's another fn, that's a third fn, and so on. And g has to be bigger, would have to be bigger than all of them, which means it would have to be bigger than something like this here. And this here, it drops like, well, it drops like 1 over x. So the only function which would be greater than all the fn's would have to grow here like 1 over x. And 1 over x is not integrable at 0. So you cannot find this g here. And, well, we had that this here is 1, and the limit integrates to 0. So the conclusion of dominant convergence really also does not hold. It's different when I take different fn's. I mean, of course. Let me correct what I draw here. So the only thing I need to change is that here I have 1 over n square. Then the error here is 1 over n. So 1 over n squared times n is 1 over n. And here I claim I really do find this function g, which is integrable. And I claim it's something like this here. So this point here lies on the curve. So this one here lies on 1 over square root of x. So 1 over n squared, square root of this is 1 over n. And 1 divided by 1 over n is n here. So this, all these curves here lie on the function curve x maps to 1 over square root of x. And 1 over square root of x is integrable at 0. That means we have found the 1 over square root of x, which is integrable. And really, the conclusion holds. So the limit of the integrals is limit of 1 over n is 0, which is mu of 0, which is mu of the limit. So this g here is really needed in dominant convergence. So well, that was an important chapter today. Monotone convergence and dominant convergence, and we will need them frequently in the course on probability theory. And next time we will start with the next chapter. See you then.